Welcome to day 47, MCT4C. Lesson is 5.9, the remainder theorem. Yesterday in class, or last class, we were taking polynomials and we found out how to divide them by binomials. And that's what today's 3-minute review is all about. So let's get at it. And hopefully now that you've done the homework and this is old hat now. I hope you're used to it. Again, the idea is we multiply by something so that when we subtract, the x cube's gone and x squared's going to work, and I put it over the other x squared. Then I multiply the other thing. Subtract. Watch your subtracting. 2 subtract -4 is +6. 2 plus 4, 6. The -3x comes down. 6x is the next thing that's going to work for us. 24. Just keep subtracting. And there are lots of places to make mistakes, so don't get too frustrated if you make some arithmetic errors. You will. There's lots of little tiny steps on this. 5 subtract -84. 5 plus 84 is 89. And then it asks us to write our questions in a division form. It's kind of like this, right? So the polynomial that we started with, is equal to the divisor, x minus 4, times the quotient, plus the remainder, right? These two statements are equivalent. That's the divisor. That was the quotient. And that's the remainder. Now, today's lesson is a little bit of a strange thing because we did all this dividing yesterday. Essentially, today we're going to be interested in only the remainder, which who really cares about the remainder? But be patient. We'll see the big picture in a couple of days. We're starting today with a little investigation. So you're actually going to stop the video here shortly and do a whole bunch of long dividing and substituting into. So for the first column, we just take 1, put it in there for x, and calculate it. And then for this next column, we're actually going to do some long division, just like we did in the 3-minute review, divide that in there and figure out what the remainder is, and then we'll write it in this table. So you should pause the video and do all that stuff. If you choose to do that in class, you'll have to come back to the video to get the conclusions, because I'm going to take up these and then we'll see a couple of homework type questions in this remainder theorem as well. So pause the video now and work. All right, I'm back. I hope you did that dividing. It probably would take you about 15 minutes, but it's good practice, and hopefully you saw the pattern. The pattern I'm about to unveil. So if you haven't tried it on your own, please stop the video and do it. But here we go. What we found, hopefully you found that, and on the next slide I'll show you all the dividing. Okay, and I should have if you remind me, I'll post this at the back of the room. But there's my divisions. Go with this. This is the first one, second one, and then down to check your work. And you can pause the video and check your work if you like. But what you are supposed to notice is that if you sub a value in, that's the same as if you did the long division and we got the remainder. So, if we wanted the remainder, and for some reason today we do, when a polynomial is divided by x minus 1, well, we could just substitute in x equals 1 into the polynomial, and then we'd get the remainder. It's a pretty neat thing. And so in this question, it says, well, here's a question, and it was divided by x plus 2. Based on your work above, write to explain how you could find the remainder without actually dividing. Well, what you'd do is you'd take the polynomial and just substitute in minus 2. Now, not 2, because remember up here was x minus 1, and when I put in 1, x minus 2, when I put in 2, and so on. So if it's x plus 2, I would substitute in minus 2, then I evaluate, and the remainder would be whatever we got when we used our calculator to evaluate that. In fact, 1. And this is what's called the remainder theorem. Okay, so in the note, in general, if some polynomial is divided by x minus k, then the remainder can be found without dividing by, well, what do? We can calculate p at k. X minus 1, we put in 1. X minus 2, we'd put in 2. When if it was x plus 2, we'd put in minus 2. But we just calculate p at k, and that's the remainder. That's the remainder. This is the remainder theorem. Why does the remainder theorem work? Well, it goes back to the division statements from the 3-minute review, right? And we saw this yesterday or last class as well, that any polynomial can be split up into a divisor, a quotient, and a remainder. So if I write that in general, I don't know what the x's and y's and stuff are what all the exponents or numbers are, but if I write it like this, a polynomial can be written as x minus k, that's the divisor, that's what we're dividing by, right? That's the divisor, times the quotient, whatever the quotient happens to be, and we have no idea because we don't even know what p at x looks like, plus the remainder. This is the same as the division statement before. But have a look at what happens if I let x equals k in here. Well, then I would start on the left-hand side. I'd have p at k, which is exactly the expression in question, right? We want to show that this is actually equal to the remainder. Well, what happens to the rest? Well, x becomes k, and you see what's going to happen here. This is going to be 0. And I don't know what q is at all, but I'm going to substitute x equals k into it, and then the remainders tag along at the end. Well, what happens is this k minus k, this gets wiped out, right? All of this stuff gets wiped out as 0. So therefore, p at k equals r. The remainder is p at k when x minus k is divided into p at x. This is the remainder theorem. And of course we can solve questions like that. And the homework today is going to be pretty short, actually. But this whole lesson, this whole remainder theorem is actually a setup for next class. Really cool math happens next class. What's the remainder when that's divided by that? Well, I guess we would say who cares, but we can answer this using the remainder theorem. We call this p at x or f at x, whatever we'd like. If we call that f at x, the remainder is, well, the k is 2 here, right? So it's f at 2. All I'd have to do is substitute in x equals 2, and then I'd get the remainder. And I pound that into a calculator, bang, 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 bang. On a calculator, I get negative 18. So I'd say, therefore, the remainder is negative 18. Okay, and I actually had a decent sentence going there for that. Another type of question, and this is just kind of a neat thinking math question, where we've got a polynomial, but there's an unknown constant in the middle of it. And I've divided this polynomial, and I'm going to call this one f at x again. I've divided f at x by x minus 4, or x plus 4. So, and the remainder is minus 82. What's the value of k? So, well, what do we know? We know that when I divide x plus 4 into that, the remainder is f at minus 4, right? That's the remainder. Well, the remainder is minus 82. Well, where do I go from here? Well, f at minus 4 is just this expression with minus 4 put in there for x. You see what's going to happen if I let x equal minus 4, then I'm going to get an expression that only has k in it, right? And then I can solve for k. This is all this thing here. That's equal to negative 82. And then some exponents and do some work on this. This is negative 64 plus 16k plus 8. See, it's turning in, every step it's turning into a grade 9 equation. There's no squares on it or anything. Collect up these like terms on the right side, collect those up, and I think that's minus 50. Add 50 to both sides. I'm going to get minus 32 over here. I'm left with 16k over here, and I'm running out of room. Hopefully you're squishing this in on your note. We're almost done, though. What's the last step? Divide by 16. I get k equals minus 2. So therefore, k equals negative 2. And that's what would be true. If I put in k is minus 2 in here and actually did the long division, the remainder would be minus 82. And we are able to sort of work backwards using the remainder theorem. All right. Well, I got a little blurb at the end here. This all seems a little odd, doesn't it? Why do we care what the remainder is? If we did care what the remainder is, why didn't we just use long division? It wasn't that tough. It was a couple of minutes, and it was kind of strange and a bit fun to divide polynomials. Why wouldn't we just divide if we were so interested in the remainder? And even the division, how does this help with our original goal of being able to graph polynomial functions? I mean, that's how we started this whole mess on polynomials, is I gave you a polynomial like that, you clunked it into the calculator, and we started looking about how to graph it without the calculator. What does this remainder theorem help us do this? Well, like this, and this is a good statement right there. What would a really awesome remainder be to help us graph this? Well, what helps us graph this is if these are all factors, right? And I know it's going to be 3 factors like this, but the question is what are these things? Well, we knew that if we were lucky enough to get a remainder of 0, a remainder of 0 means it's a factor, right? And in fact, it would be nice. Be not nice, awesome. Because then in our division statement, I'm going back to the division statement, if the remainder is 0, this part's wiped out and I'm left with only a factor and then a quotient. And usually, and we've seen this a couple times, that other part's easy to factor as well. Okay, and that's what we're thinking about. We're thinking, how do we get a remainder of 0? Because that would be awesome. The homework's in the Addison Wesley, and notice that I'll bet that you'll have time to, even with this investigation, to start the review. So if I haven't given you your pink sheets yet, make sure you ask for them, and you can start the review. Okay, that's it. Thanks for stopping by.